A single invoice sits on a clean desk, showing a charge of $84,000 for an AI model that was supposed to cost $10 to train. Cloud providers sold you a beautiful lie. They said you could fine-tune a world-class large language model for the price of a cup of coffee. But once that model hits production, the real bills start arriving. By mid-2026, enterprise postmortems have revealed a brutal truth. Over 80% of custom language model projects are failing to stay in production. It is not because they do not work. It is because they are financial black holes. Developers rush to fine-tune models using cheap, parameter-efficient shortcuts, only to realize they had stepped into a carefully laid trap. The initial training run is the cheapest part of the entire life cycle. The real cost is a hidden, continuous tax driven by mathematical constraints, data engineering pipelines, and real-world degradation. To understand why these projects fail, we have to look at the underlying math. In early 2026, AI research labs published a breakthrough finding on model linearization. It turns out that when you fine-tune a model, you are not actually teaching it entirely new logical reasoning. Think of a massive base model like a planet with immense gravitational pull. The weights of that model are held together by a tight mathematical lattice. When you fine-tune it, the optimization process is constrained by what mathematicians call an inductive bias. You are essentially pulling a small metal weight away from the planet using an elastic band. The model behaves like a linearized system around its original pre-trained weights. It is mathematically tethered to its starting point. If you try to pull it too far to make it learn complex new logic, the elastic band snaps, and the model collapses. You are paying thousands of dollars for what is essentially a formatting and style filter rather than a new brain. The second hidden cost lies in your data pipeline. AI evangelists suggest you can just dump your company documents into a training pipeline and get a specialized model. But the reality is far more tedious. A 2024 study on specialized medical question answering exposed the sheer friction of this process. To get even marginal accuracy gains, engineers could not just feed raw medical text to the model. They had to design highly complex, human-inspired curriculum strategies. They had to interleave the data, carefully balancing general knowledge with specialized medical papers in a precise order. And the reward for this massive engineering effort? A maximum accuracy gain of less than 2%. The actual hardware training cost was negligible, but the human labor required to clean, sequence, and curate the data cost tens of thousands of dollars before a single GPU even started spinning. Even if you organize your data, you run directly into a physical hardware bottleneck. Many enterprises want to fine-tune models collaboratively across different departments or private, distributed databases to protect sensitive user data. But early 2025 research on collaborative frameworks like federated sketching showed that hardware heterogeneity is a project killer. When you try to run fine-tuning across different generations of chips and servers, you hit a hard wall. The diverse performance levels of these machines limit the rank of the adapters you can use. This rank, represented by the variable R in parameter-efficient tuning, determines how much the model can actually adapt. To bypass this bottleneck, you either have to buy massive, standardized, and incredibly expensive enterprise hardware fleets, or accept a crippled model that cannot handle the complexity of your data. The moment you put your newly tuned model into the wild, you encounter the most frustrating phenomenon in machine learning: catastrophic forgetting. You spend weeks training your model to perfectly format your company's billing invoices. It works flawlessly, but then you run a test and realize that in the process of learning your billing format, the model has completely lost its ability to perform basic math, write Python scripts, or summarize emails. In the machine learning world, this is known as regression. Because the model's parameters are highly interconnected, adjusting weights to learn task B inevitably distorts the fragile circuits that allowed it to perform task A. You end up playing a perpetual game of whack-a-mole, constantly paying to patch one vulnerability only to open up 3 new ones. To prevent these hidden regressions from reaching your customers, you have to build an incredibly complex safety net. This is the continuous evaluation tax. You cannot just deploy your model and walk away. You have to construct a parallel infrastructure that constantly tests the model's outputs against a gold standard dataset every single day. This means running thousands of automated evaluation benchmarks on separate, costly server instances. When your real-world user data drifts, which always happens as customer behaviors change. You must reevaluate, recurate your data, and run the fine-tuning process all over again. The MLOps pipeline required to keep a custom model stable in production over a 12-month period can easily cost 5 times more than the initial training run. This operational reality is forcing companies to do some very hard math. They are realizing they made a fundamental architectural mistake. They chose to fine-tune a model's weights when they should have just changed its context. This is the classic debate between fine-tuning and retrieval-augmented generation, or RAG. Fine-tuning is like trying to force a student to memorize an entire encyclopedia the night before an exam. RAG, on the other hand, is giving that student an open-book exam with a highly efficient search engine. Updating a database with your company's latest information costs pennies and takes seconds. Retraining a model's static weights to memorize that same information costs thousands of dollars, takes hours, and risks corrupting the model's baseline intelligence. For 90% of business use cases, fine-tuning is an over-engineered, incredibly expensive mistake. The era of reckless AI experimentation is drawing to a close. The teams succeeding in this new landscape are not those chasing the hype of custom, proprietary models. They are the pragmatists. They understand that the base models built by multi-billion-dollar labs are already highly optimized. Instead of trying to rebuild these brains, successful engineering teams are focusing their capital on building robust data pipelines, highly efficient retrieval systems, and tiny, task-specific models that do one thing perfectly. Fine-tuning is not dead, but its status as a magic bullet is gone. Before you spend your budget on custom model weights, look closely at the math. The most valuable AI system is not the one that is custom-built, but the one you can actually afford to keep alive.